Hello everyone, and welcome to our session on the two-pointers technique. Today, we'll explore how using two pointers can optimize many array and linked list problems. Let's dive into this powerful method that simplifies complex problems and significantly reduces time complexity. Here's an overview of what we'll cover today. An introduction to the two-pointers technique. Core concepts and how the technique works. A step-by-step walkthrough of a typical algorithm. Visual demonstrations and examples to illustrate pointer movements. Benefits, challenges, and common use cases. To begin, what is the two pointers technique? It's a method where two pointers are used to traverse a data structure, typically arrays or linked lists, simultaneously. The main purpose is to simplify problems that might otherwise require nested loops, reducing the time complexity from quadratic to linear in many cases. Common problems solved by this approach include finding pairs in sorted arrays, reversing sequences, and partitioning arrays. Let's break down how it works. Pointer initialization. Start with two pointers, often one at the beginning and one at the end of the data structure. Movement rules. The pointers move toward each other or in predetermined directions based on specific conditions. Conditions and termination. The process continues until the pointers meet or a required condition is met. Advantages over brute force. This approach significantly reduces time complexity by eliminating the need for nested loops. These fundamentals set the stage for a more detailed algorithm walkthrough. Let's go through a typical algorithm using the two pointers technique. Set pointer 1, left, to index 0 and pointer 2, right, to index n-1 in an array. While pointer 1 is less than pointer 2, perform the check if the current state meets your condition, for example, if the sum of the elements at these pointers equals a target. If the condition is met, perform the necessary operation, such as recording the pair or swapping elements. Otherwise, adjust the pointers, move the left pointer to the right or the right pointer to the left based on the condition. The loop ends when the pointers cross or when the condition is satisfied. Now let's go to Visual Studio Code to implement this. So guys, we are into the Visual Studio Code. I am first going to create a demonstration function that implements the two pointers technique to solve problems on arrays efficiently. In this demonstration, I start by initializing two pointers, one called left, set to the beginning of the array, index 0, and another called right, set to the end of the array, index n-1. The goal is to use these pointers to traverse the array simultaneously, reducing the need for nested loops. Inside the function, the pointers move toward each other based on specific conditions. For instance, in a problem where I need to find a pair of numbers that add up to a target sum, I compare the sum of the elements at the left and right positions to the target. If the current sum meets the condition, I perform the necessary operation, like recording the pair or swapping elements. If it doesn't, I adjust the pointers. If the sum is too high, I decrement right to reduce the total. If it's too low, I increment left to increase the sum. This iterative process continues, checking the condition and updating the pointer positions until the pointers cross or the condition is met. By doing so, the algorithm runs in O(n) time, offering a significant improvement over the brute force O(n)² approach. In the main function, I define an example sorted array with these values and specify the target condition, for example, a target sum. I then call the function with these parameters and print the result. This effectively shows how the two pointers converge to quickly reveal the desired pair or solution. Now let's run it. This demonstration covers the core concepts of the two pointers technique, including pointer initialization, the movement rules, and termination conditions. It also highlights the benefits such as increased efficiency, simplicity in logic, and minimal extra space usage. Overall, this approach not only simplifies the problem but also ensures optimal performance in many real-world scenarios. Now let's proceed to the presentation. Now, let's discuss the benefits and use cases of the two pointers technique. It minimizes nested loops, reducing time complexity to O(n) in many scenarios. The logic is clear and concise, making the algorithm easier to implement. Space optimization. Often, the technique works in place without requiring additional space. Two-sum problems in sorted arrays. Merging two sorted arrays. detecting palindromes in strings, removing duplicates from sorted arrays. These use cases illustrate the versatility and practical value of the two pointers technique. In more advanced scenarios, the two pointers technique can be extended. It can be applied to doubly linked lists or even multidimensional arrays. The three pointers technique, useful for problems like the threesome problem. The slow and fast pointer technique, which is particularly effective for cycle detection in linked lists. Always ensure that your pointers do not cross inappropriately, and pay careful attention to boundary conditions to avoid off-by-one errors. These variations allow the technique to be adapted to a wide range of problems. Let's now focus on the performance aspects. The two pointers technique typically runs in O(n) time, as it involves a single pass through the data structure. It's minimal, usually O(1) extra space, since the operations are done in place unless additional storage is needed for result tracking. Common pitfalls. Be mindful of improperly handling pointer increments, which can lead to infinite loops, and ensure that overlapping conditions do not cause missed edge cases. Thoroughly test your algorithm with various input sizes and clearly document the logic behind pointer movements. This slide provides a concise overview of these performance considerations. To wrap up, the two pointers technique is a powerful tool that can optimize algorithms by reducing nested loops and simplifying code. It is versatile and widely applicable, from basic pair searches to more complex operations in linked lists and multidimensional arrays. I now welcome any questions or comments about the technique, its implementation, or specific use cases you might be curious about. Thank you for your attention. See you in the next session.